Hi, this is Alana Lynn doing Lab 3 video report, Constant Velocity Motion. I videotaped my friend Will longboarding, and my result was that my Python model provided good predictions of his motion. Okay, so here's my video and tracker. I started the clip after he was in motion, and I stopped it before he slowed or stopped because the goal was constant velocity. The total time of the clip was 0.83 seconds, with a time step of about 0.33 because I cropped around the times where he was moving in the frame. I gauged his average position by tracking his belly button because that is his approximate center of mass. To give tracker a length scale, I put the calibration stick down the length of the longboard and labeled it with 0.0927 meters. Then I placed the axis with the origin at Will's center of mass in his first frame and aligned the x-axis with his motion to simplify calculations. This way, his initial position is the origin, and he has movement only in the x direction. I needed to adapt the model to better represent the situation, so I gathered this information. To find the mass, I weighed Will and his longboard and converted it to kilograms. The initial position was dependent on the axis in tracker, so I set that to the origin. Therefore, it's the origin in this model too. The average velocity is only in the x direction because of the way it's set up in tracker. So I calculated the x value using the final position in tracker and divided it by the time of the clip segment. The time step is 0.01, which is small to optimize the model's accuracy. Since velocity is supposed to be constant, the model must have a net force of 0. So I changed that too. Here you can see where I integrated those values into the code. I also had to put Newton's second law into the velocity equation. The velocity equals the original velocity plus the net force divided by the object's mass multiplied by delta t. The ball will still move at a constant velocity because the net force is 0. When I run the module, the ball moves at a constant velocity, to the right. Much like the longboard, the graph shows the ball's x position over time. It starts at the origin and steadily moves in the positive direction. I exported the data from Vital and Tracker into Excel and made a combination time versus position plot that shows the model in blue and the actual in red. The model fits the actual motion pretty well. What if I had changed the axes in Tracker? If I tilt them more, there will be a varying y velocity component, as you can see from the various distances of the points from the x-axis. Moving the origin will also affect the model. These changes change the table values for the x and y positions. In Python, this is changed numerically in initial conditions. The starting position is different and the ball velocity's direction has changed. When I run the module, the ball starts in a different place and goes in a different direction. The graph shows this through a change in the y-intercept and a change in slope, because it only shows the x position versus time. What does it mean? This experiment showed that through the comparison of a controlled idealized model, we can prove that objects remain moving with the same magnitude and direction until a force acts on them. Since I could control the model, I set the force equal to 0 and saw a constant velocity. The actual data was very similar to the model, proving the second law.